notes for AP Calculus on the topic of parametric formulas without the graphing calculator. So this one says we've got a particle moves along the graph of y equals cosine f by x. So there's y, and notice this is a normal equation. It's not parametric, because it's just got x and y in it. And then it tells you the x component of acceleration is always 2. So the way we can translate that is x double prime of t. If you put it in function notation, it's probably a little easier. Or you could write x squared t, d squared x, t squared, if you want to write the rate of change notation, is always 2. So that's a constant of 2. And then it tells you at time 1, the particle's at the point 4, negative 1. So again, here's your x component. Here's your y component. And the velocity vector of the particle, and there should be the word is in there, is 5, 0. So oftentimes they'll write the vectors with the notation like this, but occasionally they might use parentheses instead, but it means the same thing. Again, here's the x component of acceleration, x prime, and here's the y component, y prime. So that, in other words, the velocity, I should say, the x component of velocity, the y component of velocity, the velocity vector. So it says find the x and y coordinates of the position in terms of t. So we're trying to get back to the position functions for both x and y, which oftentimes is what we start with, but here we kind of have to work in reverse. So let's start with what we know here, that the acceleration, or the x double prime of t, is always 2. So if we just multiply both of these, both sides of the equation, by dt, and then we can integrate. And when you integrate x double prime, that'll get us back to velocity x prime of the x component. And when you integrate 2, we get to t as our variable, and then plus our unknown constant. And we're going to have another unknown constant in this problem, so I'm going to refer to this one as c sub 1. So we don't get them mixed up there. And now, in order to solve for that constant, we can use the fact that we know at time 1, the x component, x prime, is 5. So we can substitute that in. We can say we know x prime is 5. When t is equal to 1. And so you can see you subtract the 2, and we get c sub 1 equals 3. So now we can put that right back in here. So now we know the velocity vector for the x coordinate, x prime of t, is equal to 2t, and now we just figured out c is 3, plus 3. And now we can, to get back to position from velocity, again multiply both sides by dt, and then integrate both sides. So that'll give us back to x of t, which is one of the things we want, the position function, equal to 2, and you integrate t, you get t squared over 2, plus 3t, and then plus another unknown constant, I'll call it c sub 2. You can see the 2's reduce out here. So you just get t squared plus 3t plus c sub 2. And then again, to figure this out, notice we know the x coordinate is 4 at time 1. So we can substitute that in, of position, because it's at that point. So we can say 4 1, so 1 squared plus 3 times 1 plus our other constant c sub 2. So notice we get 4 equals, that's 1 plus 3, that's 4 plus c sub 2. And we subtract 4. In this case, this constant happens to end up being 0. So now we've got part of our answer here. For position, we know x of t, the x-coordinate in terms of t, remember it is t squared plus 3t. So that c sub 2 is 0. Okay, so that's the x-coordinate in terms of t. And then to find the y-coordinate, well, it may not be super obvious what to do here. It's a little different here, but we know y in terms of x, right? And we just figured out x of t, or x is equal to t squared plus 3t. T squared plus 3t. So again, remember you could write this also as just x equals t squared plus 3t. Might be able to see. Then we can substitute that directly in for x right there. So we get y equals cosine of pi times t squared plus 3t. And notice you could leave your answer technically like that. It is in terms of t. Or if you want to make it a little simpler to work with, you could distribute out the pi and get cosine of pi t squared plus 3 pi t. So there's our y-coordinate in terms of t. All right, let's take a look at part B on the same question here. Part B says find the magnitude of the velocity vector. When its position is 10 and there's the x, negative 1 is the y. Okay. So it's a little different terminology here, but another way of saying the magnitude of the velocity vector is really just another name for the speed. Okay. Because remember, velocity can be positive or negative. In this case, there's 2 components to it, but we're looking at the overall speed when it says the magnitude of the velocity vector. Just another way you might see it worded the same thing. So, for the speed on these, and remember if we go back to the formulas at the very beginning of your notes here, remember speed is the square root of the velocity at that time squared plus the velocity, the y-coordinate of velocity at that time squared. Okay, so the key is this is the position right here, 10, negative 1. And we need to get back to the velocity, the magnitude of it. So we need to, in this case, the general formula would be the square root of x prime. We need to know what the time is. Sometime I'll call it a for now, squared, plus y prime of a squared. That'll give us the speed. So to figure out that time, let's use the fact that we know the position here. So let's look and see which of these would be easier to work with here, the x or the y, to solve for the time. So the x equation looks a little simpler, doesn't it? T squared plus 3t. So let's try to use that one here. X of t equals t squared plus 3t. So since this is the position x, we want it to be 10. We can substitute that in right here for the position and use this to help us solve for the time. So if we get that equal to 0 first, subtract the 10, t squared plus 3t minus 10. And then factor it, t plus 5 and t minus 2. We get 2 times negative 5 and 2. Remember, we're not going to have negative times. We're not going backwards in time here, so the only answer that makes sense is t equals 2. Now this next part, you don't have to do, but if you want to confirm that the y-coordinate is negative 1, you could plug in 2 here. So this is an optional step, just to confirm this is the right time. Plug in 2 for t right here, and let's see what happens. So we had y of t, or in this case y of 2, would be, again, you can write y equals or y of t equals, either way. Cosine of pi t squared so pi 2 squared plus 3 pi times t. So let's see what that gives us here. So that's 4 pi plus 6 pi. That's cosine of over here. That's cosine of 10 pi. And 10 pi is the same place as 0. And you can see cosine there would be 1. So, I apologize here, I had a little typo on this. This was supposed to be a positive 1 here, not a negative 1. So that does give you that position there at that time too. So now, we know the time is 2 here. So this is going to be the square root. X prime of 2 squared plus y prime of 2 squared. All right, so we need to know x prime of 2 and y prime of 2. So let's go ahead and find those. Start with the easier one, x prime of t. Well, that would just be 2t plus 3, the derivative here, and that's the x component of our velocity. And then if we substitute in 2 times 2 plus 3, so x prime of 2 is 7. So this will be 7 squared. And then for y prime of t, just have to use the chain rule here. So we'll have negative sign of pi t squared plus 3 pi t, and then times, sorry, I'm running out of room here, let me just erase this real quick. A derivative of the inside, which would be 2 pi t plus 3 pi. And then if we substitute in 2 into that, sine, if you substitute 2 in here, that's again going to be 10 pi. And sine of 10 pi times, that's going to be 2 there, that's going to be 7 pi. But the sine of 10 pi, notice, is 0, so that wipes out this whole thing. So y prime of 2 would just be 0. So it's going to be plus 0 squared. So in this case, that's just the square root of 49, which is 7. So it's not always going to work out to be an integer like that, but in this case it does. So that would be the magnitude of the velocity vector when in the particles at that position. All right, let's take a look at another problem here. So this one says, we've got the position of a remote-controlled car moving along a flat surface as modeled by the parametric equations. So here it does give you the position of the x and the y, and it says, what is the rate of change of y with respect to x? So that's just another way of saying dy dx. Rate of change of y with respect to x. Specifically, when t equals 4 in this case. That's what they're asking for. So remember on the parametric ones, so we've got two different components. It's going to be dy dt divided by dx dt. And in this case, we want it specifically at time 4. So if we want this at time 4, we basically have to substitute in t equals 4 into both of these. Or in our particular case, we would use the notation y prime of 4, because it's written in function notation here, divided by x prime of 4. Just two different ways of writing our derivative here. So let's go ahead and find those. So x prime of t would equal 2t minus 5. And then if we substitute 4 into that, prime of 4 would be 2 times 4 minus 5. So x prime of 4 would equal 8 minus 5, 3. And then y of t, let's rewrite that first. And rewrite it as y of t equals t squared plus 9 to the 1/2. So when we take the derivative, using the power rule here first, be 1/2 t squared plus 9 to the negative 1/2. And then using the chain rule, times the derivative inside times 2t. And then when you simplify that, you see the 2's reduce out. And you get y prime of t would just be t divided by, in radical form, that would be the square root of t squared plus 9. So then for y prime of 4, we're substituting 4 there, so it'll be 4 divided by square root of 4 squared plus 9. So that's 4 divided by, that's 16 plus 9 is 25. So it ends up being 4/5. So we can put those in there. Y prime of 4 we just figured out is 4/5. And divided by x prime of 4 we figured out is 3. And then to simplify it, that's the same as 4/5 divided by 3 is the same as multiplying by the reciprocal, 1/3. In this case, nothing reduces, so we get 4 over 5 times 3 is 15. So that would be dy dx, specifically t equals 4. Or, this is just really just another way of saying the slope of a tangent line. It all could have been worded that way. What's the slope of a tangent line when at time t equals 4? And you get the same answer. It's asking for it just in a slightly different way in terms of the wording. All right, let's take a look at part B on this one. Okay, so for part B, it says the position of a remote control car, we got the same situation. At what time t, so we're looking for a time, is the tangent line, the path of the remote control car, parallel to the y-axis? All right, so let's think about what that means by sketching the little x and y-axis here. So here's our y-axis here. So if it says the tangent line is going to be parallel to that, that means it's going to have to be vertical. Okay. So when it says parallel to the y-axis, it's really just another way of asking for what time does it have a vertical tangent. Or if it said parallel to the x-axis, it'd really be asking you for a horizontal tangent line. And the key is, remember, for a vertical tangent line, the derivative, the slope of the tangent line, is undefined. And on these parametric ones, to make it undefined, well, the denominator has to be 0. Remember the denominator comes from dx dt. So we got that was 2t minus 5. So when it's undefined, in this case x prime of t, or dx dt, however you want to write it, that's what has to equal 0. So we already got that was 2t minus 5. And if you solve it, add the 5 divided by 2, you get t equals 5 over 2. And in this case, we won't give any units for time here, so seconds, minutes, we don't know what it is. All right, and let's go one more. It's a little bit different here. So most of these involve vectors with the position vector, velocity vector, acceleration vector, all these parametric ones. But occasionally they might just give you some other function that doesn't necessarily relate to position, velocity, or acceleration. And if it has more than one component, like these have 2 components, it's called a vector valued function, is another name for it. So here, g of t, we don't know if this is position, velocity, acceleration. It could be something else that has 2 components like this. And so here's the first component, comma, here's the second component. What's the value of g prime of 3? So all you do, kind of like you would for a piecewise function, for g prime of t, you just take the derivative of each one separately, just like you would if you're going from position to velocity vector or the velocity vector to acceleration vector. It works the same way. So the derivative of the first one, using the chain rule here, the derivative of sine is cosine. And using the chain rule, multiplying by the derivative of pi t is pi. And then, again, derivative of this one, again, using the chain rule here, t squared is the function inside. The e to the t squared part, just like e to the x, stays the same. But times the derivative of t squared is 2t using the chain rule. So that would be g prime of t. If we needed the second derivative, you would just take the derivative of each of these. Here, you just use the chain rule again. Here, you'd have to use the product and chain rule. But here, we're only asked for the first derivative at 3, so now we just have to substitute 3 to this and evaluate what it's going to be. So it'll be cosine of 3 pi. So we can simplify this now. This is the AP test. You wouldn't necessarily have to simplify the second one, because it's all pure numbers, but you would have to simplify the first one here. So cosine of 3 pi, well, 3 pi is the same place as pi here. So cosine, just like at pi, is -1. But then it's times the pi, so you get negative pi. And then if we simplify this one, we get 6 e to the 9th. So those would be the two components of the derivative. And depending on the context of the problem, this one's kind of an abstract one. There would give you two different components of something that don't necessarily mean the x and y, or horizontal and vertical components, like they do for parametric ones. And that concludes the notes for AP Calculus on the topic of parametric functions without the graphing calculator.